Woohoo! We are recording. This is 9.5, the product rule and the quotient rule. And so in this section, we're going to talk about some shortcuts, kind of, as to how to calculate derivatives without having to use, dun dun dun, the definition of the derivative. Now, the definition of the derivative is still the gold standard, but thankfully, dozens, if not hundreds or thousands of mathematicians before us have worked very hard to come up with some shortcuts. So these formulas get us out of having to do the long version of the definition of the derivative. The downside is that, as you can tell with the quotient rule, it gets fairly complicated when you're looking for a formula, but they're not that hard to learn. So let's go through them. The product rule tells us how to take the derivative of the product of two expressions. And this is the way it's traditionally written. And believe it or not, I look at this and I have warm, happy thoughts of all the times I took calculus. U's and V's aren't my favorite way to do it, but it is pretty traditional. The other way they do it is M and N. So rather than, have fun with letters that look just like each other, I decided to go with colors. So if f of x is the product of two expressions, a blue expression and a pink expression, to take the derivative, basically they just take turns. Now, this is not what a lot of people would guess. A lot of people would guess you just take the derivative of each one, but that's not the way it works out. And again, this comes directly from the definition of the derivative. So if you actually work this out, the product rule is not that difficult to get to. The quotient rule is a little bit harder, but in the rest of chapter 9, we will talk about other techniques that would help you derive these. So you could, by the end of chapter 9, you'd be able to derive both of these formulas. But rather than have you do that, let's just go ahead and use them. So the product rule specifically, if I have two expressions and they're multiplied together, then they take turns. And the way that I figured out to write up this card is if you see a D, that means take the derivative. So we're going to take the derivative of the blue one times the pink one. So derivative of the first times the second, regular second. And then we take the regular first times the derivative of the pink one, the derivative of the second. So in other words, they take turns. The quotient rule is a little less obvious or simple to express. So let's talk about what's going on here. And this is the more traditional way to write it up with U's and V's. I've got it with pink and purple. Or pink and blue, sorry. I've got a blue expression on top in the numerator and a pink expression in the denominator. This is a quotient. It's basically a fraction. And they do take turns. You take the derivative of the one that's on top first times the second, and the derivative of the bottom one second times the first. But notice there's a really big difference. When you're using a product rule, they're just multiplied together, you add them. And when you're looking at the quotient rule, where they're set up in a rational expression or in a fraction, you're dividing them, you subtract. So big difference there. And then the other thing that happens is the denominator just doubles down. So you take turns, the derivative of the top times the bottom, the top times the derivative of the bottom, but then down in the denominator, you square whatever was there. So it gets way worse. So if you can kind of look ahead and it doesn't shock you so much that you're shocked into, it doesn't completely freeze you, imagine a second derivative. The second derivative would be, this would be our new top, and this would be the bottom, and then it gets worse and worse. So taking derivatives of rational expressions can be very, very frustrating. It can be very time consuming. And in fact, that's something later on in chapter 9, hopefully we will get to this, I will be able to show you an alternate method, a different way of looking at it. Rather than as a quotient, I will show you how to look at it as using exponents, because the denominator is basically whatever the denominator is to the negative first power. So there is a way to work with that. So let's go ahead and get started. I started off, the product rule doesn't tend to cause a lot of trouble for folks. So a lot of times the product rule comes pretty quickly. I've got a single example, but obviously if you would like to see more examples, please let me know. If you want to work some of these out in office hours, that would be awesome. So here, let me position this. Okay. I've got the product of two binomials, very straightforward. If I want to take the derivative, oh, and it might help if I say this is going to be the blue and this is going to be the pink, right? I'm just going to match them up, matchy-matchy with what I've got on my card, the blue times the pink. Then the derivative is going to be the blue, but this is going to be the derivative of the blue times the pink, plain pink, and then we add to that, now this time it's plain blue, no derivative, but we're going to take the derivative of the pink one. So just in writing it out, we see that taking the derivative of a product expands it a lot. Now, it is likely that what's going to happen is it's actually going to shrink down and maybe even be smaller. But to begin with, we're going to expand it a lot. So give yourself lots of room. Okay, so my blue expression is x minus 3. So I'm going to take the derivative of that. Now, I'm going to show you, this is secret, how to describe this. This is very informal way to write it. So if you're going to be doing math in front of very fancy people, do not do this step. But this is something that I and my friends all did. We put this little derivative, this little prime notation around the expression we're going to take the derivative of. The expression we're going to differentiate. This is like slang. This is not nice. A lot of people would actually be horrified that I'm showing you this, but I found it very useful as a student, so I'm showing it to you. So x minus 3 is my blue. I'm going to take the derivative of the blue times the pink, times the second one, plain. Then the plain blue one. Oops. I almost did a plus there. I got very excited about all my pluses. Sorry about that. So x minus 3, and then we're going to take the derivative of x plus 2. So they're taking turns differentiating. Now, I set this one up to be pretty nice. It's pretty straightforward. What is the derivative of x minus 3? Remember, if you've got terms, x minus 3, we take the derivative of x is 1. And the derivative of 3 is, because it's a constant, 0. And we don't do anything to the pink one in this one. And then for the second part, don't touch the x minus 3, but let's take the derivative of the pink one. Derivative of x is 1. And then plus derivative of 2 is 0. Well, this is really nice. And I set it up to be really nice. This is just 1. And this, in fact, is just 1. Now, sometimes you'll have 2 or 5 or something more, but in this case, that's what I have. So I just have 1 times this, so that's x plus 2, and then 1 times this plus x minus 3, and that's 2x minus 1. So let us check this. Now, sometimes it'll be easy to check differentiation, sometimes it won't be. In this case, it's pretty straightforward. And how am I going to check it? Well, what I could do is I can take my original function, x minus 3 times the quantity x plus 2, and multiply it out using FOIL. So this is just regular old function. So I've got x times x, x squared, outer, plus 2x, inner, minus 3x, and then last, minus 6. And again with my pluses. X plus 2x minus 3x is minus x minus 6. So if that's f of x, then what's the derivative of x? So it's the derivative of x squared. So that's 2x. The derivative of the opposite of x, which is -1, just the coefficient. And then this would be 0. So we get 2x minus 1. Woohoo! Now, in this case, I would probably suggest that multiplying two binomials out, if they're polynomials, is so straightforward. I would probably do it this way rather than bother with the product rule. I wanted to pick a situation, a case where it was very easy to do it in both ways and not spend too much time, so you could kind of see how it works. But there will be times when you're multiplying two expressions together and there's just no good way to multiply them out, or there's a reason why you can't multiply them out or something else. So it's good to have the product rule kind of tucked away and ready to go. Okay, so product rule down. Now let's do the quotient rule. For the quotient rule, I actually have two examples because this is not easy to learn. It's just kind of clunky and long. So the way to think about the quotient rule is, I think, let me scooch this down a little bit. Let me scooch this down a little bit and point out that the product rule, when we're multiplying, has a plus, and the quotient rule, when we're dividing, has a minus. And it's really important to remember those two. So it's kind of a compare and contrast situation. Again, I'm going to go ahead and I'm going to use my somewhat slangish terminology. Give myself, I need a lot more room than that. There we go. Okay, top is blue, because that's how I did it on the card. You can use whatever color you like. I'm going to do blue first, and then pink. Pink is my denominator. And so that's the basic setup. I'm going to multiply one of the derivatives times one of the planes, minus the other derivative times the other plane, all over the denominator squared. So in fact, if you want to just skip right to it, you could always just go straight to the x plus 5, the quantity squared, because we know the denominator is going to get squared. Then up on top, we have to remember that in this case, so in the product rule, it kind of doesn't matter since we're adding. Doesn't matter which one you go first. Because we're subtracting here, you have to do the derivative of the top first and the derivative of the bottom second. And this is the point where every math teacher on the planet is supposed to remember the expression low d high, high d low, I think. It never worked for me. I always had trouble remembering it. But if you know that expression, or you want to go look it up, or you want to ask me in office hours, we can figure it out together. There is a cute little rhyme that helps people remember this. I just try to remember it by visually remembering the picture. So we want the derivative of x squared minus 4x first times just the plane x plus 5. Then we're going to take the x squared minus 4x plane times the derivative of x plus 5. All right, so the derivatives are on the outside like that. Okay. So piece by piece. I'm not going to try to be slick and go through it. Also, you'll notice that your brain is seeing the x plus 5s and wanting to cancel them. Don't do it, because this is the derivative of x plus 5, so it's not a complete x plus 5. It won't reduce the way you expect it to. So, x plus 5 in the denominator, we're stuck with it. Okay, derivative of x squared minus 4x. Derivative of x squared is 2x. Derivative of minus 4x is minus 4. And then we've just got the plain x plus 5. Okay, now I'm going to subtract. I've got the plain x squared minus 4x, and then the derivative of this, which I'm thrilled to see, the derivative of x is 1, the derivative plus 5 is 0. Okay, that is the setup. Let's see if we can make anything reasonable out of this. Okay, so let's see. Here, pretty much what I'm going to have to do, and again, I know these are winking at each other, but because of this minus, you can't cancel these two. There's no good way to do it. Now, sometimes something really beautiful happens over here. I did not set it up that beautiful way. I decided to go ahead and give you an ugly one just because most of them are ugly, and I want to show you that you can get through it. We could do it together. Woohoo! So, 2x minus 4 times the quantity x plus 5. So right here, I've got 2x times x, that's 2x squared. 2x times plus 5 plus 10x. Minus 4 times x minus 4x. Minus 4 times 5 minus 20. And we're subtracting. And then notice this whole thing equals just the number 1. So we're just subtracting x squared minus 4x, because this whole thing is just times 1. And it's all over x plus 5, the quantity squared. So I've got 2x squared plus 10. Oh, you know what? I can combine those two, can't I? Woohoo! I'm getting a correction tape workout today. 10x minus 4x is 6x minus 20. Now I'm going to subtract, right? Make sure the subtraction goes all the way through. Minus x squared plus 4x. Okay, we're almost there. Like I said, quotient rule, sometimes kind of brutal. 2x squared minus x squared, 6x plus 4x plus 10x, and then minus 20 all by itself. Next up, the last step is to see whether or not we can reduce. And there are a lot of ways to do that. You could go ahead and try factoring this. You could use the AC test, right? You multiply 1 times negative 20 to get negative 20, and you see what numbers multiplied together to make negative 20 give you 10. You can use the quadratic formula to see if this factors at all. And if you do, there is a sneaky way to do it. Let me show you. So if we look at this, if no one has ever shown you this, when you're just trying to do a quick and dirty, does this even factor? If this is a case where it doesn't obviously factor. Oh, rabbit fur. Always with the rabbit fur. So, if we have ax squared plus bx plus c, and you set it equal to 0, but you don't, right? This is the quadratic formula. You've got the opposite of b plus or minus radical b squared minus 4ac all over 2a. You want to look at b squared minus 4ac. b squared minus 4ac. In this is going to be 100 minus 4 times negative 20 times 1. So that's going to be plus 80. So that's 180. Is that a perfect square? If that is not a perfect square, then this does not factor. So that is one way you could do it. Another way is you could work through the AC method. You could just straight up use the quadratic formula and find out what you get. You could use, there's an X method, there's trial and error. There are a lot of ways to check that this does not factor nicely, so you can't reduce this. So this is the final answer. It's the final answer. And we're on the final problem. Yay! Are you guys excited? I'm so excited. Yay! I'm so excited. We're on the last one. Now, this is a case where if you are, if you're feeling relaxed and you've had enough sleep and you've eaten your vegetables and all those wonderful things, then you will look at this function and first off, you'll see that that's weird. It says 3. It should, I wrote 2 and it should be 3. But you'll notice that this function could be reduced. Notice that there's a 3 common to both factors on top and in fact common to the bottom as well. So if you would like to, if you see this ahead of time, go ahead and factor it out. I'm not going to, because I'm going to show you that it works out at the end anyway. You just end up having to factor the whole thing at the end. So this is another case where math will take care of the mess. It's just, if you notice it, go ahead and take care of it. Go ahead and reduce it. It'll make it easier. But if you don't notice it, we'll figure it out at the end. Okay, so feel free, if you're working along with this, feel free to go ahead and work this out. And if you do see how to reduce it, go ahead and reduce it. If you don't, then don't worry about it, and we will reduce it at the end. Woohoo! I love all the second chances that math gives you. I know everyone thinks that math is very, very hard and picky and mean, and it never gives second chances. But from my perspective, oh my goodness, it gives second chances all the time. Okay, again, I'm going to use my color coding because it does help me. Again, if it doesn't help you, don't use it. So I've got my 2, and again, because this is a quotient and not a product, this is a minus in the middle. Oh, it looks that looks like an axolotl, doesn't it? I mean, if you look, maybe it's just too late at night, but I swear that look, 2 little eyeballs and a little mouth, and then this is like its little body, and these are do you have any idea what I'm talking about? Probably not. An axolotl is like a little newt that lives like in caves. It's aquatic or semi-aquatic. They're very adorable. I could not probably spell it. It has a lot of vowels, and it has an X and at least an L or 2. Axolotl, yeah. And some A's and some O's and some other stuff is going on. It's really much cuter than the name, although it is fun to say, axolotl. Okay, I'm going to stop saying axolotl, and I'm going to come back to the math, which is to remind you that in a quotient, we've got this little mouth, which is our subtraction. We've got multiplication here, and we're going to start off with the derivative of the top times the regular bottom, and then the regular top times the derivative of the bottom. And then down the denominator, we're going to get whatever's down there, and it's going to double down. We're going to square it. Okay, so I had to take the derivative of 3x squared minus 3x, and then plane 6x minus 3, and then plane 3x squared minus 3x, and then the derivative of 6x minus 3. Now, at a certain point, there's this moment where you're doing this thinking, oh, this is so terrible. And then I'll remind you, believe it or not, this is a shortcut. This is a shortcut. And that in fact, the really hard version would be if you're asked to do it using this. Because you can imagine that if this is your function, then suddenly you've got complex fractions running around everywhere. So this really is a shortcut, believe it or not. Okay, let's see what we got. I got the derivative of this. So 3x squared becomes 6x. You got it. Minus 3x becomes minus 3. And then this really interesting thing happens. And I am going to use my colors because at this point you're going to look at this and go, wait a minute. That's the exact same thing wow, the denominator is just the derivative of the numerator. Whoa, mind blown. Okay, so this is our derivative of the blue. Then we got the derivative of the pink. So the regular blue, 3x squared minus 3x. And then the derivative of this guy is just going to be 6. You got it, 6. Then I've got 6x minus 3, the quantity squared. Okay. Again, this and this are going to wink at you. They're going to be like, hey, cancel me. I will change your life. It's going to be so easy. Just cancel everything and we're done. Remember the rule. You can only cancel on the left if you can also cancel on the right. This minus means you have to be able to cancel on both sides. We can't, so we're stuck. So I'm going to go ahead and FOIL the heck out of this. 6x times 6x is 36x squared. Minus 3 times 6x is minus 18x. Minus 3 times 6x is minus 18x. Since they're the same, I'm basically doing a perfect square. Minus 3 times minus 3 is plus 9. I'm going to subtract 6 times this, so that's 18x squared minus 18x. This is all over 6x minus 3 squared. Now, you notice that at no time am I multiplying out the denominator. The reason for that is I want it in this form so that if it does cancel, I'll be able to cancel it easily. I believe factored form is best. I know not everyone agrees with me, so if you're in someone else's class, it may be that they ask you to multiply this out, in which case do that. Use FOIL or use the perfect square formula. But for me, leave this thing. This thing should stay factored. Okay, I got 36x squared minus 36x plus 9 minus 18x squared plus 18x. Notice this. Remember, this is going to go all the way through and change all the signs. Okay, 36x squared minus 18x squared is 18x squared. Minus 36x plus 18x is minus 18x. And then the 9 is just by itself. Now up top, I can factor out a 9, which I'm going to do. Sorry, my brain just stopped there for a second. It's like, now what do? I don't know. I thought you were paying attention. I don't know. Okay, so this is very exciting. Now, what do we do down here? And this is why I wanted to leave it like this so we could talk about this, because I'm not sure if this has ever come up for you. What do you do when you want to factor something and it's squared? Well, you got a couple options. Possibly the easiest one is to write this out as 2 different factors and factor them out. But let me try showing you something and see how it flies. So here's my squared. And inside I've got 6x minus 3. So that's 3 times the quantity 2x minus 1. What do you think? What do you think about 6x minus 3 being 3 times the quantity 2x minus 1? And they're both inside the square. So I haven't done anything. I've just split the 3 out. Kind of, sort of. I actually, even though you're not all watching this, I'm recording this a good few hours before anyone sees it because it's going to take forever to upload into YouTube. So, but I can actually feel some people going, whoa, I'm not sure about that. So I just split this up inside of the square, and then I have to opera the square. So then I get, let's come down over here, 9 times the quantity 2x squared minus 2x plus 1 all over, and then the 3 gets squared and the 2x minus 1 gets squared. And then I realize that I've got 9 times the quantity 2x squared minus 2x plus 1 all over 9, 2x minus 1, the quantity squared. And I can cancel those 9s. And I'm going to get 2x squared minus 2x plus 1 all over 2x minus 1, the quantity squared. Now, I know this looks like it should reduce. It does not. 2x minus 1 does not go into this. This does not factor nicely. If we do b squared, so negative 2 squared, that's 4. Minus 4 times 2 times 1. 4 times 2 is 8 times 1 is 8. So 4 minus 8 is negative 4. Inside a square root, you got nothing. This does not factor using the number system we're using. So this is the final answer. Final answer. Doo-doo-doo. But I want to sneak back up over here and talk about what was happening at the beginning. So, note, 3x squared minus 3x all over 6x minus 3 is equal to 3 times the quantity x squared minus x all over 3 times the quantity 2x minus 1, which, if we had seen in the beginning, is just x squared minus x all over 2x minus 1. So this is just a little note. I'm going to leave this up here. So let's take a look at what happened. If I had seen that I can reduce this, then I would get to this point. And then keep in mind, this is just a little bit simpler than this. So all of this would have been easier. And notice here that we only had to cancel 3's. By the time we were done, when we used the whole formula, what did we have to cancel? We had to cancel 9's. So in fact, the 3's that we did not reduce got worse by the end of the problem. So this is kind of my advertising to say, hey, if you see that you can reduce something and you're sure that it reduces, it is definitely worth your time to reduce it before you start the problem. Even though the math will take care of it and you don't have to see it, it means more work at the end. So it's up to you. It's either going to be work up front or work at the end. Your choice. The other cool thing is notice when I cancel my 3's, what's the denominator? It's 2x minus 1. What do we end up in the denominator? 2x minus 1, of course, squared, because it's the quotient rule. So, woohoo! I should stop talking because we're nearly to 35 minutes. Yeah, these problems with calculus, they get longer and longer. But you guys are amazing and awesome, and if you did not fall asleep in the middle of all of that, then I am very, very impressed, because I very nearly fell asleep, even though I was in the middle of doing it. That's the product rule and the quotient rule, and they are shortcuts. And to answer the question, no, I don't know a single person who enjoys them. I mean, the product rule is really okay. The quotient rule is just a lot to get through. So make sure you've got lots and lots of, good recycled paper. Use both sides if you're not taking pictures for people. And, get some exercise, get some sunshine. Make sure you have some fun, get lots of sleep, and know that you are absolutely so awesome. Math on, guys. Math on.